So now we're going to get an introduction to waves. And the topics that we'll cover in this video are, we're going to define what a wave is and talk about the terms related to waves, talk about wave motion, and what happens when waves interact with each other, which would be superposition and interference, and then introduce the idea of energy in waves. So a wave is a disturbance that carries energy from one place to another. It can be a sound wave, a water wave, earthquakes have waves, light is a wave, but it's all carrying energy from wherever it started to somewhere new. And some of the vocabulary you'll hear along with waves are period, wavelength, wave velocity, and amplitude. And period is just like it was in circular motion and simple harmonic motion. It's the amount of time for one cycle, and in this case a cycle is one complete wave motion. Wavelength is a distance, and it's the distance between two parts of the wave that are identical. So it could be two crests, or two troughs, or two parts where it crosses the equilibrium. Be careful with that one, because it'll cross twice in one wavelength. Wave velocity is the speed that the wave moves from one place to another, and we call that propagation. You'll hear that over and over again. And the amplitude is similar to amplitude in simple harmonic motion. It's the distance the wave is away from the equilibrium position. And you can think of the equilibrium position as an axis right down the middle, where if there was no wave, nice flat line, that's equilibrium. So there's a wave equation. The velocity of the wave is equal to its frequency times its wavelength. Nice straightforward equation. The frequency is in hertz and the wavelength is in meters. Wavelengths are going to come in all sorts of lengths. You've got little tiny wavelengths for light, you've got great big wavelengths for waves and radio waves and things like that. So pay close attention to the units on your wavelengths. And so here's an example. An earthquake produces a wave with a frequency of 10 hertz. If it takes 15 seconds for that wave to travel from the epicenter of the earthquake to some nearby city, and the city's 80 kilometers away, what's the wavelength of the wave? Well, to start off with, we know the frequency, we're trying to find the wavelength, but we don't know the velocity yet. So we'll have to figure out velocity from the distance and time that's given in the problem. So the first step is to find velocity with distance over time, and then use that velocity in the wave equation to find the wavelength. There are two basic types of wave motion, and I know we talked about propagation being the speed of the motion, and now we've got direction of propagation and displacement. So transverse wave is like a water wave that you see. It's a sine wave. It moves away from that center mark. So it's got a displacement away from the center mark. It's perpendicular to it. So the displacement is actually perpendicular to the direction of motion. Now a longitudinal wave is like a pulse in a slinky. And this is sound waves are longitudinal. And the displacement is going to be in the same direction as the propagation. So if you squash a slinky and let it go, you'll see that little compressed area move down the slinky, and that is a longitudinal wave. And some examples of these kinds of wave: light is a transverse wave, and sound is a longitudinal wave. Both types of waves are found in earthquake waves and water waves. The surface waves of water are mostly transverse, but underneath there's quite a bit of the longitudinal types. So waves interact, and they interact with surfaces, and they also interact with each other, and we're going to talk a little bit about what happens when waves interact with each other. When they come together, it's called superposition, and all it really is you're summing the amplitudes of those two waves when they come together. The amplitude is related to how much energy is in the wave, so when it comes together, the energy either increases or decreases. And in the two examples you see here, we have constructive interference, where all the peaks are meeting up and all the troughs are meeting up, which makes the wave twice as tall. And then destructive interference is going to be anywhere where the peaks meet the troughs and they cancel each other out. And you can have anything in between. They're not always lined up beautifully, but you can get some constructive and some destructive. The examples you have here are completely constructive and completely destructive. So here's kind of an example of how you would handle that. If you have the red and green waves and you want to find out what the actual resultant wave would be, you just go along and pick places along the timeline there on the x-axis, and you add the amplitude. So you can see on the y-axis that you add the negative 0.9 and negative 2.1, and the new wave is going to be at negative 3. The next over at about almost halfway across, you've got both of them intersecting at a displacement value of 3, so sum it together, you get a 6, and you just go along and do that all along the wave to find the amplitude of the new wave. Now there is a special case when waves interfere, and you can get what's called a standing wave. And it's called a standing wave because it appears to be still, and it just vibrates back and forth. It's really going one direction and coming back, going one direction and coming back, and it happens most often in tubes and on strings that are tied on the end. It's how we get music out of horns and pianos and all those wonderful musical instruments. Some of the vocabulary that goes along with this is an antinode is the maximum amplitude, and a node is where there is no amplitude. And you'll be counting nodes and antinodes, and there's actually 2 antinodes in a full wave. And like I said, this is one of the basic reasons we have musical instruments. This is the physics behind it. Is you get these standing waves in tubes and on strings, and they create notes. And those notes, those of you that are musicians, this will be the physics for that. You probably already know it. But you have a fundamental frequency, and that's going to be with the longest wavelength possible on a string, and usually that's half a wave. And then after that, the harmonics are just multiples of that fundamental frequency. It's how many whole and half waves can you get on your string or in your tube. Now another musical quantity that goes along with waves are beats, and beats come from another type of interference. The waves are close in frequency, and when they superpose, they have constructive and destructive interference, so that you hear soft and loud sounds in a beat pattern. And the equation for this is just the difference between those 2 frequencies. So as an example, I've got a tuning fork of 464 hertz and another one of 460 hertz, and if you hit them at the same time, you'll hear the wah-wah sound. And if you do the math, you'll hear it 4 times every second. So it's and our last topic is intensity. How strong is the wave? How much energy is it carrying? And it's going to be proportional to the square of the amplitude. And it really, the effect that energy has depends on the amplitude of the wave and how much area is affected and how long the wave is in that area. So there's some different things that come into play when you're talking about the effects of the intensity. So intensity is power divided by area, and the intensity is measured in watts per meter squared, and the power is in watts, and the area of propagation is in meters squared. So I have an example for you. Energy from the sun arrives at the earth with an intensity of 1.3 kilowatts per meter squared. And then how long does it take for 1.8 times 10 to the 6 joules of energy to arrive in a 1 square meter area. And so we have intensity as power over the area. I have intensity, I have area, but I don't have power. But then, you think about it for a minute and you realize that, oh, well, power is just energy over time. So I do have energy, and that's convenient because I really want the time. How long does it take? And so I rearrange my equation and plug the items that I have given in, and I get 1,384 seconds. Alrighty, bye-bye.